Alrighty, I think we're going to go ahead and get things started. So welcome to the June Astro Night. So just a couple announcements before we go ahead and get things started. First things first, we are a little bit light on volunteers tonight, so unfortunately we will not be having a star party after the talk tonight. I'm very sorry about that, but to make up for that, we have an absolutely fantastic talk. And so we're going to be having a talk. This talk is going to be roughly an hour, and then we'll have about 15-20 minutes for questions after that. So I think we're going to go ahead and get things started. So this is Ben Coughenour, and he is a postdoctoral researcher at the UC Berkeley Space Sciences Lab, working with data from the New Star satellite to learn all about black holes, neutron stars, and accreting white dwarfs. And so he went to the University of Michigan as an undergraduate before earning his PhD at Wayne State University in Detroit. And so his talk will be all about whether or not black holes get dizzy. Go ahead and take it away then.
Okay. Hopefully everyone can, oh, there we go. Everyone can hear me okay? We're good? All right. This is what I'm looking for. So yeah, my talk is titled, Do Black Holes Get Dizzy? Because it turns out a thing that astronomers try to do is to measure the spin of a black hole, whether or not they're spinning, whether or not those poor black holes get dizzy. And I will say, thank you all for coming tonight. It's awesome actually being here on campus because I work at Space Sciences Lab up the hill. So this is like my second or third time actually on UC Berkeley's campus, other than just passing through. So cool to actually be here in an on-campus building, and cool to have all of you here, and thank you all for coming. Just to give a quick outline of what I'll be talking about. This one to work. So I figured 2 years of not using this remote and not replacing the batteries, I wonder if it's going to give up just as my talk starts. Okay, so a talk outline is we're going to talk about what a black hole is, because if you want to know whether or not they get dizzy, it's nice to talk about what it actually means to talk about a black hole. We'll also talk about how it is that we learn about black holes in science, how astronomers try to study, what techniques do we use, and what is it that we find out? Do black holes spin, and if so, do they get dizzy? So just to talk about what is a black hole, sort of the classical way to do that is to carry out a thought experiment. If you imagine yourself somewhere up high at a good elevation where you've got nothing else in the way, and if we're going to be physicists, we can pretend to ignore all the effects like drag or worrying about whether or not air is going to slow it down. But if you were to take a baseball and throw it as fast as you could, if you're anything like me, it won't go very far. If you're anything like an Oakland A's baseball player, it might go a bit further. But what if you could throw that baseball really fast, or as this thought experiment is often referred to, Newton's cannon? If you could launch a cannonball off of your high peak or top of a tall building, how far could you get it to go? And you begin to realize when you think about it that if there's no air resistance, there's no drag, if you really launch that sucker, it's going to start traveling a good distance and falling along the curvature of the Earth's surface. What if you put a little bit more oomph on it? If you could launch it even faster, that projectile would actually travel and fall at the exact same rate as the Earth's curvature falls away beneath it. And you would have found yourself launching something into orbit. It would come right back and hit you in the back of the head. If you launched it a little bit further, well, no worries. It will still be in Earth's orbit. It'll just get a little bit further away and form, rather than a circular orbit, an elliptical orbit, and then come right back and get to where it returned. But if you launched it even faster than that, you get to what we like to call escape velocity, where you've launched that projectile so quickly that it's never going to actually return back to Earth. It will just continue to drift out into space. And we've launched quite a few things. The famous example is both of the Voyager missions, which are now at the outer edges of the solar system that have left Earth's gravity, you could say. Just again, Newton's cannons, this time we've got a nice cannonball. Several different speeds you could have in orbit, but if you launch it fast enough, it's going to escape orbit, it's going to escape that body that it started off at, and that's what we term as escape velocity. It's a really easy thing to calculate. It's just this equation right here. It depends on the mass of the body that you're launching something off of, that big capital M. And on the bottom side is the radius. The smaller the object is for a given mass, the tougher it will be to achieve escape velocity, to launch something out into space, not just into orbit, but out of orbit. Business Insider put together this really cool graphic, which is just doing that calculation for all the bodies of our solar system, or I should say all of the planets of our solar system. To leave Earth behind, not to go into orbit, but to actually leave Earth, you need to achieve 25,000 miles per hour to get escape velocity. Jupiter would be a lot harder than that as the biggest body in our solar system. The Sun has an escape velocity of just over just about 1.4 million miles per hour. This is our thought experiment about the black hole, but I haven't talked about anything outside of our solar system yet. So what about a black hole? You could imagine something that was so massive or so small in terms of smaller radius makes it tougher to launch off of, that something moving as quickly as the speed of light wouldn't be able to escape, wouldn't match that escape velocity. This idea was brought up in 1784, before we had a good measurement of the speed of light, by an astronomer, John Mitchell, and that was just using Newton's gravity. He was thinking about, again, very much in that same way, throwing a baseball off of a star, but the fastest baseball you could throw would be a light particle. There is a bit of a misnomer here that the way that light moves away from a body like a star or a black hole, it doesn't move away, slow down, stop, and then come back if it doesn't achieve escape velocity. So it's a bit of an error in that conceptual, that's where the idea breaks down. But you can still kind of think of that as a definition for what a black hole is, something that's so massive, so dense, that light itself cannot escape. If we really want to talk about a black hole more strictly, we have to talk about Albert Einstein, who in 1915, at this point already a pretty famous physicist, not necessarily an international celebrity at this point, published his general theory of relativity, which rewrote the rules for how gravity works. And at that moment, it didn't seem like it was going to change that much, because Einstein's gravity, general relativity, looks a lot like Newtonian gravity. It was a huge deal though, because no one had questioned Newton's gravity before. Pretty much the only way that Newton's gravity started breaking down was with the planet Mercury's orbit not acting quite as well as it should. People proposed there being a planet called Vulcan closer to the sun. By the way, if you're talking about general relativity, we always show this sort of bowling ball on a trampoline idea of how an object that has a mass will affect space-time, the space around it. Just a friendly reminder though, space-time is 3, but really actually technically 4-dimensional. So if we're going to start drawing our trampolines a little bit better, they look like this. Don't worry though, that makes my head hurt too. So we won't have to imagine space-time is 3-dimensional. So Einstein put out general relativity. Just a few months later, another physicist looking at Einstein's field equations for how space-time should work. He wanted to solve that in an actual scenario, not just flat space, but let's say you put something into that flat space. And being a physicist, he took the easiest possible, or at least so it would seem, the easiest possible situation. Just one object, one point mass, dropped into space-time. How does that affect the curvature of space around that object? And his solutions looked a lot like Newtonian gravity at a distance, but as we got closer and closer to that point mass, that's when general relativity started to take hold. As you got really close to that point mass, that's when the equations started to look like utter nonsense. At a certain radius away from that point mass, or distance away, we now call that the Schwarzschild radius, that R sub s. Really close to that object. And just to think about this, g is a tiny number, Newton's gravitational constant, m is the mass of the object, and then we're dividing that by speed of light, a massive number squared. So this is a really tiny radius for a given mass. And at that point, his solution essentially went to infinity. And at first people thought that was nonsensical and didn't think too much about it. But as we become to think about black holes as being an astrophysical possibility, mostly in the 60s, people realized that that Schwarzschild radius represented the event horizon. The point from which, if you were to turn on a flashlight, light's not going anywhere other than back into the black hole. That's your sort of stopping point. So here's our friendly Earth in its gravitational potential well, bowling ball on a trampoline representing general relativity. The black hole is like someone just punched a hole in space-time itself, and you're left with that sort of never-ending well that you can't climb out of, even if you're traveling at the speed of light. A fun thing to think about what a black hole is, if we're going to talk about that event horizon, is a black hole could theoretically be anything. If you take any mass and you condense it down to the right size, you'll have a black hole. All you need is to take all of that object's mass and get it inside that object's Schwarzschild radius. So a good example for the Earth, if you wanted to turn the Earth into a black hole, you'd have to shrink it at the same mass. You have to condense all of that mass into a ball with a radius of 9 millimeters. Pretty tiny, like a cue ball or a pool ball, if you think about it. Jupiter, quite a bit bigger. You'd have to take all of Jupiter's mass, squeeze it into a ball with a radius of 3 meters. The Sun, 3 kilometers. So if you took the Sun, something 100 times wider than the Earth, and you squeezed it into a city block, it would become a black hole. And then we have some actual astrophysical black holes with pretty well measured masses, and some fun pictures of them. I should say that first picture is not an actual picture, but a fun artist representation. Cygnus X1 was one of the first black hole candidates, people thinking that we were really looking at an astrophysical black hole. Its Schwarzschild radius is about 44 kilometers, so tens of kilometers. There's a black hole we saw a picture of not too long ago that's got, it's the supermassive black hole, the center of our galaxy, Sagittarius A star. It's about 8% the distance between the Earth and the Sun is the size of that black hole in terms of its radius. And M87, another famous supermassive black hole, it's larger than the size of our solar system, just because it's that massive. So you can turn anything into a black hole if you wanted to. And I went across a few different size scales there, and I think it's worth keeping in mind that black holes sort of come in 2 different groups. You have stellar mass black holes, which are sort of the regular ones that we understand a little bit better. And then there are our supermassive black holes, like Sagittarius A star or M87 star, that are millions, if not billions, of solar masses. I said that we understand stellar mass black holes a little bit better. We at least understand how they form. I'm going to show you next. This is a poster that's going to be in every single high school astronomy class or college astronomy, introductory astronomy lab, which sort of sums up how stars live their lives. And it's a pretty awesome image just for that. But if we're interested in forming black holes, we really only have to pay attention to the first few tracks at the very top. On the left of this chart, by the way, is the beginning of a star's lifetime. On the right is the end of a star's lifetime. Lower mass stars are at the bottom, higher mass stars are up at the top. So if you were to take the most massive star you could make, or some of the most massive stars you could make, most stars will live short lifetimes and likely end their lives in a supernova, sort of a shock or rebound once the core is done fusing elements into heavier and heavier elements. It'll eventually run out of fuel and sort of collapse on itself, which could send a shockwave out and cause a supernova, or it could collapse on itself into a black hole, sort of a failed supernova, as that material gets swallowed up by the black hole. That's how you form a stellar mass black hole. It's just the end of a very massive star's life that didn't totally get destroyed by annihilated by its own supernova climactic ending. Supermassive black holes, we don't understand particularly how they form. We know that they should have formed similarly perhaps to stellar mass black holes. You could imagine the very first stars in our universe collapsing into black holes and then growing over the course of our entire universe, 13 and some change billion years. They might grow into a black hole that could weigh 4 million times the mass of our sun, like Sagittarius A star does, or billions of times the mass of our sun, like M87 star does. But in order to do that, you'd have to be feeding that black hole at the absolute limit that you could, and then you need that black hole to run into a few other massive black holes to get it to be that hefty at our age in the universe. The other possibility is that these are primordial black holes, that they start at thousands of times the mass of our sun from the very beginning of our universe, and they've just been growing from there. That at least makes it more of a regular black hole diet for those who have grown to massive sizes. By the way, I have 2 images here that don't have too much to do with black holes, other than one is the cosmic microwave background, which shows all of these slightly different colors. Those are less than 1% change, less than 0.1%, less than 0.01% changes in the temperature of our early universe, the first light we can detect. And you notice that there's a bunch of little tiny dots. Well, those are from density changes in the earlier universe, some of those most dense areas might have collapsed to form black holes that sunk to the center of the most massive galaxies that are the huge black holes that we see today. The other image that I'm showing you is, you might recognize the James Webb Space Telescope, which launched was on Christmas Day of last year, and has been unfolding those mirrors, those giant gold mirrors, and sort of doing its calibration since this summer. We're going to get our first science results from the James Webb Space Telescope. One of the exciting things about WST is it might help us answer that question looking far back in time and measuring the masses of the earliest black holes. But until WST comes online, until we've looked at that data, that's sort of an unanswered question. We really don't know if we're going to find early massive black holes or not. The next question is, we've talked about stellar mass black holes, supermassive black holes, what a black hole is. Does a black hole spin? Well, I would probably think so. It might seem like a strange thing, but most celestial bodies do spin. The Earth spins once every 24 hours. That's our rotation around our rotational axis from our North Pole through our South Pole. Jupiter, it turns out, is not only the biggest, but also the fastest rotating planet in our solar system. It only takes less than 10 hours to make one trip around. So days can be pretty quick on Jupiter. And our sun rotates as well. We think every star rotates. Our sun's a little bit slower and actually has differential rotation at different latitudes, but that's a whole other topic. So pretty much everything does rotate about its center. You would expect a black hole to as well. The difference being, on Earth, we can watch the oceans and continents spin around. On Jupiter, we get to see its clouds move around. On the sun, we watch sunspots move across the surface of the sun. The black hole, you don't get to see that. So how would we know if a black hole is spinning if we don't get to see any surface, if there's nothing for us to look at? Well, in general relativity, unlike Newtonian's Newton gravity, the spin of an object actually affects the gravity around it. It affects the space-time around it. We call that frame drag. So if an object is spinning, it will have a slightly different gravitational pull. It's a slight difference, but it'll have a different pull to things around it. In the case of the Earth, you could do a fun experiment. If you measured, if you stepped on a scale on a train moving against Earth's rotation to the west, and you measured yourself, you should weigh a little bit less moving towards the west than if you repeated the exact same thing, moving along the direction of Earth's rotation to the east. Now, I don't think you can go and buy any scale that's going to notice that tiny difference, but it should still be true. NASA, indeed, spent a bunch of money to launch a satellite to try and test exactly this principle and get as close as they could to testing general relativity here on Earth, rather than around the sun or in any other sort of extreme environment. And indeed, NASA's Gravity Probe B, using 4 different gyroscopes, did detect ever so slight changes in the directions of those gyroscopes that could only be explained, and was perfectly explained, by frame dragging due to the Earth's rotation. There's actually a way larger effect due to differential height between, just from one side of the satellite to the other, the differences in gravity in that terms of its height from the Earth's pole. But they did also notice and could measure the frame dragging effect as well. There's also a little bit of an interesting upper limit. You think of the speed of light as the universe's speed limit. It turns out that there's a spin speed limit as well. This is true for everyday objects, just because if you spin something fast enough, it'll eventually get ripped apart by that angular momentum. I've watched YouTube videos of guys spinning an apple so quickly that the apple just rips apart once you get it up to a couple hundred revolutions per second. Unfortunately, there was a space telescope, the Hitomi X-ray satellite, that started spinning too quickly. When they tried to correct for that spin, there was a sign error, so they actually sped it up, and that poor satellite ripped itself apart by its own angular momentum, which is sort of a tragic story in trying to learn more about space. For black holes, they also have a speed limit in terms of their rotation. We call that, I love this term, the law of cosmic censorship. Unfortunately, it's not really a great term, and it's not totally a law, but the idea is if you spin a black hole rapidly enough, it deforms its singularity to the point that you could have the singularity getting outside the event horizon, which, like the event horizon and then the singularity at the center, are the two things that define what a black hole is. So how could you have the singularity outside of the event horizon? It's a head scratcher, and people don't like it is, I think, the best there. They can come up with solutions where it's allowed to have a black hole spinning that quickly, but people don't, people seriously doubt whether that's astrophysically possible. So we have this upper limit on, and there are good reasons for it. I wouldn't call it necessarily a law, but there are very good reasons for this speed limit for black holes. The two equations I have up here, just to go through them really quickly. J is the angular momentum that is just saying it has to be less than gm squared, the mass of the black hole over the speed of light. On the other side, I'm introducing the dimensionless spin parameter A, which has to be between 0 and 1, because nobody wants to write down gm squared over c. If we just write down A, that's one number, and it stays between 0 and 1. And that's a good way to talk about how quickly a black hole is spinning, whether it's a little black hole or a supermassive black hole. So I'll reference that number A, the spin parameter, again, and that's just an idea of what it means. So then the next question is, so do black holes spin? Probably, and we might be able to observe this through frame dragging. How do we observe black holes in general? If I was giving this talk a few years ago, this would be a lot harder of a question to answer, but now we've all seen black holes, so it's not really as tough of a thing. These are two images of the two black holes we have direct images of. On the left is Sagittarius A star, our own Milky Way galaxy's supermassive black hole. It's about 4 million times the mass of our sun. On the right, we have M87 star, which is, I think, 6.5 billion times the mass of our sun, but it's in a different galaxy way far away from us. So it's unbelievable that we can take these images just because the engineering and data analysis feat to be able to have these images seems almost impossible. And to get a good idea of how impossible, hopefully this video works okay, the Event Horizon Telescope created this video, which is going to take us from one of their radio arrays on Earth, look up in the summer sky towards the constellations of Sagittarius and Scorpius, and looking towards the center of our Milky Way galaxy. And we're going to zoom in past the millions of stars between us and there. We're going to continue zooming in right into the galactic center through gas and dust that makes up a lot of the center of our Milky Way galaxy. We're going to continue zooming into a bright radio source that shows up at the very center of our galaxy. And zooming in even further, we get to see, finally, that orange fluffy donut ring that we've all come to see. The reason that this is so incredible in terms of confirming black holes exist and work like we think they do, that dark spot at the center of this ring, that only exists, we're not looking at a ring of material that just happens to be facing us. It looks like a ring because the light coming from the material, as it's just falling into that black hole, is being warped around the black hole and then set in our direction. And that shadow at the center is only there because the black hole has an event horizon. And any of the light that was going in that direction or coming from that direction fell into the black hole and didn't get to us. The size of this event, that shadow works out perfectly with what we expected, knowing the mass of Sagittarius A star. It's just a little bit larger than the event horizon. This is the strongest and most direct evidence that we have yet, confirming general relativity, and even more crazy, the most extreme possible scenario for general relativity. And again, just the technical feat, I still get mind-boggled by this, trying to even think about it. The Event Horizon Telescope used a network of arrays of radio dishes spread across the Earth, and they even waited for the Earth to rotate so that they could fill more of that out. And in doing so, they essentially created an Earth-sized telescope, and were able to pull together all of that data. The size of that orange ring that you're seeing would be about equivalent to the size of a donut on the moon, which maybe doesn't sound that crazy, but remember the moon is only about a quarter the size of the Earth, and all of those features that you see on the surface of the moon, even in this nice, pretty good image of the moon, are all, country or continent size, if not ocean size. And we're zooming into a donut on the moon from here on Earth, which is just absolutely incredible. But before we had those pictures, we could still talk quite a bit about black holes and how we observe them. This is a video that's going to show, it was done by observers from Mauna Kea, the mountaintop in Hawaii, and looking with the Tech telescopes at a series of stars right at the galactic center. And you'll notice the year is the number in the top right corner. As we advance through time over about 20 years, they watch these stars swinging around through space, through an empty point in space that's highlighted by that white star cartoon there at the center. Those orbits look a lot like orbits of comets orbiting around our sun in our own solar system. Those comets are, millions of times less massive than our sun at the center. And in the same way, these stars are millions of times less massive than the object at the center. That star coordinate was drawn because there's a bright radio source coming right from that. That bright radio emission is coming from material falling into the black hole. So we actually could confirm, just by watching these stars, the mass of the object at the center of the Milky Way. And we're pretty confident for it to be a black hole, even before we had the picture. With M87, we were pretty sure that that supermassive black hole was there too. You're looking at actually two different images that are sort of slapped on top of each other. All of the white light is the galaxy in which that supermassive black hole resides, M87. That sort of bluish line that's sticking out from the top of it is in radio, and it's falsely colored to show that image above the galaxy. It's about as wide as the galaxy, or as long as the galaxy is itself, extending thousands of light years out into space coming from the center of that galaxy. And that is a jet of relativistic particles being launched by something ridiculously energetic at the center of that galaxy, which we now know to be that supermassive black hole. We've also listened for black holes. Again, I couldn't have done this just 10 years ago. But in 2015, we had the first detection of two black holes emerging. And if I can unmute this. Hopefully everybody can hear that at least a little bit. That sort of chirp, or like a water drop, is the sped up audio from the waves that they detected at the gravitational wave observatories at LIGO at Hanford, Washington, Livingston, Louisiana. They've been running for quite some time, since 2015, when that first detection was made, and now all of these blue dots that you see here are black hole mergers that have been detected. There are almost 100 of them now. Each line, vertical line on that chart, has two black holes, which were the two black holes before the merger, and then the higher up you go, the more massive you go. And that arrow drawing to the top blue dot shows you the mass of the remnant black hole after the merger. So we can listen for black holes if they collide with one another, if they merge with one another. We've now taken direct images of black holes, but before we could do any of that, we had to rely on normal astronomy, which was looking at electromagnetic radiation. And in our case, we had to look for black holes interacting with something, because they don't give off any light by their very nature. So it's not a particularly easy thing to see. Sorry, that's a little bit cut off, and I imagine the rest of this will be a little bit too. So the supermassive black holes we've seen large enough to take images of with, granted, an Earth-sized telescope. When it comes to stellar mass black holes that are much closer to home, even with a much larger than Earth-sized telescope, we have no luck taking pictures because these objects are only tens of kilometers across and still thousands of light years away. So direct images are just not going to be a possibility. And yet we've been studying these things for almost 50 years now, but doing it in just a different way. We're not relying on just the images we get. But just so you don't have to take my word for it, I'm working on some black hole data right now, and that's the image I get. It looks fun. Those are all false colors. The lighter colors represent, especially that white dot, it's just how bright it is. The detector got completely saturated at that center, which is what that white dot represents. If I showed you a more reasonable picture of this, it would just look like a white smudge. There's no actual detail in that. It's just screaming at the detector, hi, I'm here, look at me, I'm bright. In that image are all of the things happening around the black hole, the companion star, all of the other things going on. But we can't resolve any of it. It's all just a really bright point that gets so bright that it's sort of diffracting across the detector. So if we can't trust an image, because an image just looks like a bright spot, what can we do? We have to rely on spectroscopy. Spectroscopy works as, I think the cartoon version is taking a prism and breaking apart light into its different colors. So white light gets spread out into an entire rainbow. And these are the spectra, the rainbows of a bunch of different stars, a bunch of different types of stars. And you'll notice, if you look at them long enough, they look a bit different. The stars near the top are a little bit brighter in the blue than they are in the red. The stars on the bottom, it's the opposite. They're brighter towards the red. So by breaking apart light, we can not just tell how much of certain colors there are, we can even, as well, look for discrete features in those spectrums. Those dark shadows you see hiding amongst the colors are different spectral lines that correspond to different elements that are absorbing light at that exact particular color, that exact particular wavelength. And we can actually tell the chemical abundances of atmospheres of stars if we can match all of those dark lines that we see to lines that we can test here in a laboratory, which is how we've learned what stars are often made of. But when we're talking about doing spectroscopy on a black hole, it's not quite as easy as using a prism. If we go back to this schematic of our stellar black holes and how we see them, we're looking for stellar mass black holes that are usually cannibalizing a partner. They're taking away the outer envelope of their neighborhood star. And I should say most stars are actually partners, especially most massive stars. They're not born alone, so our sun is actually a little bit weird or unique in that it has no companion stars. It's just a single individual star. If you're a Star Wars fan and you like the idea of seeing two suns in the sky, there are probably lots of planets in our galaxy that get to see two sunsets exactly like that. And especially massive stars are more likely to be born with companions, and they'll orbit one another throughout their lifetimes. And if one of those massive stars ends up ending its life and becoming a black hole, it might interact with its companion, stealing material from the outer atmosphere of that companion. That material will form a disk in the plane of the orbit of those two stars, the black hole and its companion. And it might even, if it's a messy eater, for example, spew some of that material as a relativistic jet out in either direction. But as this material falls in towards the black hole, it gets ridiculously hot. And if I was to show you this picture in optical light, you would only see the companion star, which is much bigger physically, and therefore it will appear brighter through a normal telescope. But if we look at X-rays, we won't see the companion star so much, but we'll see the accretion disk around the black hole, and in particular, the innermost accretion disk. And so we have to look not in the regular colors of the electromagnetic spectrum, what we think of as visible light. We have to look to the left on this diagram at higher energies, shorter wavelengths. We have to look at X-rays. This is fun, just a good diagram of how electromagnetic radiation works. Radio waves and infrared is everything to the right of visible light. On the left, we get our ultraviolet X-rays and gamma rays. And just to think about how temperature affects how what part of the electromagnetic spectrum you'll show up at. If you think about thermal goggles and how it shows people, even if it's completely dark in the room, that's because the human body is warm enough to glow in the infrared part of the electromagnetic spectrum, not hot enough to glow in actually glow in visible light. If you heat up something on the stove, it might be hot enough to glow in visible light. If you heat up something that tends to millions of degrees, or sorry, tens of millions of degrees, it will start to shine primarily in X-rays, which is how these accretion disks appear to us. And to look at X-rays, we have to go into space, which is probably a good thing. X-rays don't get through Earth's atmosphere very well, which is great. We all have a lot higher radiation doses and have to worry a lot more about our skin if we have X-rays coming through the atmosphere. So we have to launch satellites into space, and all of these satellites look particularly elongated and a bit weird. And that's because each of these X-ray satellites is focusing X-rays. The thing you would think about X-rays is that they go through things, right? If you think about your standard X-ray image, it goes right through all the flesh on your hand, but it gets stopped by the dense bone, which is how an X-ray imager works. If we were to build, for example, the Hubble Space Telescope has a huge mirror on it, or the James Webb, I showed you the mirror earlier. If we built a huge mirror and put it in space, all the X-rays would go straight through it, and it would be utterly useless. So we have to sort of gently nudge with a bunch of concentric cones. We have to nudge those X-rays together ever so gently. They're very particular, so that we can get them to focus some distance away on the detector. And this is NuSTAR, which is the satellite I worked most with. It launched in 2012. That mast, the long ladder-looking bit between the two parts of the satellite, is about 10 meters, so 30 feet long. And on the side closest to us is where all of the mirrors are that are doing that gentle nudging. And they're focusing the X-rays all the way down that ladder on the other side of the satellite where where the detectors are. And every X-ray satellite has to work in a similar way if it's focusing its optics, which is sort of a tricky thing to do. But what we're looking for isn't getting a particularly clear image. What we really want is the spectrum. And so here I'm plotting the spectrum. You can think of this as, say, red light on the left and blue light on the right. The lower energy X-rays are showing up on the left, higher energy X-rays showing up on the right. And you can tell, just looking at the spectrum of a black hole, that it's brighter in the red part of the X-ray spectrum. And those, we call them soft or lower energy X-rays. But exactly the shape of that spectrum, we can then apply a model to. And I'm really hoping this shows up. Hopefully people can see. I've drawn a pretty curvy red line on the left side and then a pretty flat slanted line across the rest of it. And if you add the two of those together, it almost perfectly matches the spectrum that we have. And those two different lines represent two different physical things. The curvy line in red on the left is the accretion disk. And based on the size, shape, and the cutoff of that accretion disk, we can learn a lot about the inner temperature of material right before it falls into the black hole, as well as the size of the accretion disk. The rest of that is coming from quantization is usually the word. You can think of it as stuff above the accretion disk, a corona of a black hole. We say the word corona a lot because above the accretion disk and at the base of the jet, you're going to have incredibly quickly moving, incredibly hot material, mostly ions and electrons, that are going to interact with any other photons and bump them up to higher energies, which is why we kind of get that flat looking line across the top of it. I'm not going to go too much into the physics about that. So it looks like a good fit here because the bright blue line almost exactly matches the black data points across our spectrum. But if I were to show you the residuals or the differences between those two, or if I showed you the data divided by that model that I plotted across it, you'll get a different view. And all of a sudden, it doesn't look like we've done a very good job at all. There's quite a few odd features showing up in the spectrum. And it's actually a good thing that those odd features are showing up. Although I do have to say it's because our system is a whole lot more complicated than I originally showed you. We're not just seeing these individual parts of the accretion disk and individual parts above the black hole shining directly to us. They're shining in every direction. And as a result, they're going to interact with one another. In particular, if there's the base of a jet directly above the black hole, or a cloud of relativistic electrons higher up above the black hole, some of the photons that emits are going to be sent right down onto the accretion disk. I've drawn curved lines here, which I'm really proud of, because those light travel paths will actually be curved by the black hole's gravity. Some of that material is going to bounce up off the accretion disk, and we call that reflection. And the reflection features that we see are going to look like a few emission lines. But normally an emission line just looks like a spike, a straight spike that's perfectly symmetric and very narrow. These are several emission lines in a number of famous black holes that have been well studied. And they don't look narrow and they don't look symmetric. In fact, they look rather weird. And that's because it's coming from the inner accretion disk, and that single line gets warped by the environment in which it's in. So it's moving relativistically around the black hole, so you'll get Doppler effects because of that. We think of Doppler effects with sound, but if you move fast enough, you can get Doppler effects with light as well. It's then being relativistically beamed toward us from the side of the material that's moving toward us on that side of the accretion disk, and the material on the other side of the accretion disk is going to be fainter as a result, so that makes it even more asymmetric. Then you'll also have a general relativistic redshift. If you're really close to a black hole and a photon, some light crawls out of that potential, gravitational potential, it actually gets stretched out and it changes color as a result. So if you had a friend standing at the inner accretion disk right next to a black hole and they shined a white light at you, to them it would look white, but by the time it got to you, that white light would get stretched out and it would appear red. Or even if they had a blue light, by the time it gets to you, it would appear red. So all of these effects totally distort this line, but the good thing is we can actually account for all of those effects, and in doing so, we're actually measuring the inner accretion disk. And the reason this has something to do with the black hole is because if you remember me saying that in general relativity, an object's spin is going to affect the space-time around it, that actually means that a black hole spin affects the accretion disk around it. That last orbit that's possible, that's stable under general relativity before material immediately flushes down into the black hole, that last orbit relies on whether or not the black hole is spinning. On the top image on the left, it's a black hole that's spinning in the opposite direction of its accretion disk. And so the material in the accretion disk will be very far away before it immediately plunges down into the black hole. I have a non-spinning black hole in the middle on the left. You can see the accretion disk has got quite a lot closer. That last stable orbit of material before it takes the plunge gets quite a bit closer. And then our favorite is when you have a rapidly spinning black hole, the accretion disk can actually extend right down exactly to the event horizon if you have a black hole at that spinning speed limit I talked about before. You can also see different spectra that this produces. If you're looking at the line on the left part of that on these charts on the right-hand side, you can see that the shape of the line is quite a bit different because of these relativistic effects. And so when we measure the line profile, it's giving us a picture of what the accretion disk looks like, and then it tells us about the black hole spin. And using this method, we've been able to measure a couple dozen or so black hole spins, some to pretty incredible accuracy, because we can see the accretion disk getting right down to the very last orbit just outside the event horizon, which means we must have a rapidly spinning black hole. I will say, I talked about A, which is the dimensionless spin parameter a little bit earlier. It goes from -1 to 1. I also mentioned that A can really only go from 0 to 1. So 0 to 1 is all of the cases where the accretion disk spins in the same direction as the black hole. 0 to -1 is when the accretion disk is moving in the opposite direction of the black hole's spin, which is why that goes there. But just from this chart, it looks like almost every black hole, except for just a few, has their black hole spin and accretion disk aligned the right way. And most of them are spinning very rapidly, above 0.5 or so. And that's generally been the case. We think most black holes are spinning rapidly, and physicists are happy. Just to talk a little bit about my own work, I got this data that I showed you before, and this is that same black hole and its big spread out iron line between, say, 4 and 10 keV. If you're looking at that, it's the big hump or bump on the left side of that graph. I tried measuring the spin of this, and within a couple of weeks of getting this data and analyzing this data and fitting models to this data, I constrained the spin to the point where this black line, the lower it goes, means the better the model fits the data, and the x-axis here is that spin parameter A, and moving towards the right means a more rapidly spinning black hole. So there we go, I measured a really rapidly spinning black hole. I was really happy and ready to write my paper, or so I thought. It turns out that the assumptions that you make about the geometry of both the corona that's above the black hole, where those really high energy photons, those X-rays are coming from, and the accretion disk itself will tell you whether or not you have to make assumptions about that geometry in order to measure this black hole spin. And it turns out that in my particular case, when I let loose some of those assumptions, in the case of my black hole, I've drawn that star way up near the top of our funny little cartoon. And what that means, unfortunately, is the highest energy X-rays that I'm looking at are coming from either material that's way above the black hole and above the accretion disk, or from a very extended corona, a huge cloud of material way above the black hole or the accretion disk. And that distance is so much larger than the distance between the accretion disk and the black hole that we don't get to actually constrain the spin for this particular black hole that I'm working on, XH 1803. But that's okay, because it's just one observation, and the height of that corona and the shape and geometry of that corona will change over time. So we'll check back in and hopefully get a good spin measurement of this black hole at another time. There are also other ways to spin the black hole. You don't just have to look for this reflection. You can look for a time lag, which is what I'm trying to show with this chart here. This is ridiculously complicated, and I feel like I'm running a bit late on time, so I'm not going to go into too much detail. But the idea is that we can actually measure light echoes coming from the inner part of the accretion disk. We see some change that happens first, and then a short time later, we see a change happening outer in the accretion disk at a different energy. And if you follow those light echoes, just like if you walk into a cave and you shout your name and you hear an echo come back, if you had a stopwatch, you could calculate based on the speed of sound how big that cave is based on how long that echo took place. And very much the same way with light echoes, going back to this picture of reflection, if that star flashes first, some of that flash is going to go right at us, and then some of that flash is going to bounce off the accretion disk and then get sent to us. And the delay that we measure is the light travel time between those 2 points. And knowing that delay and knowing the speed of light, we can calculate precisely the size of the inner accretion region. This is tough to do though. It's mostly been used for the outer accretion region in supermassive black holes. It's starting to get used on stellar mass black holes in X-rays, but we don't have a spin measurement from this yet. We do have a lot of good other evidence taken from using timing techniques and looking for light echoes. There's another way though that we can try to measure spins. I showed you this before. This is our masses of the stellar graveyard. These are the black hole mergers that have combined. Well, it turns out that those chirps that we heard are also not just affected by the mass of the 2 black holes that are merging together, but their spins. This is straight from one of the LIGO science papers. It's a pretty complicated chart, so I won't take too long or focus on it for too long. But based on the effective in-spiral that LIGO measures, they can tell that either one of the black holes was spinning and it was lined up with the orbit of the 2 black holes before they merge, or if they don't get a large spin measurement, that means that either both of the black holes weren't spinning at all, or they might have both been spinning, but they were not aligned with the orbit of the 2 black holes and their orbit. And if you look at this, what's called the effective spin measurement for all of the LIGO measurements that we have, not too far there we go. Over time, this is just looking at observing Ronnet 3, which is broken into 2 different parts. Now the effective spin is on the y-axis, and drawing a line straight through, you can see the 0 point. Most of these points fall along 0, which means that the mergers that we're seeing, we are either looking at black holes that aren't merging, or sorry, that aren't spinning before they merge, or we're looking at black holes that are merging, but their spins are misaligned from one another and misaligned from the orbital plane before they merged. And that's a bit different than what we saw with our individual black hole measurements, which was taken from X-rays using reflection. So I just put these 2 charts next to one another, and this is actually a big debate and sort of an argument that's going on in astrophysics right now. And these 2 communities are not too particularly pleased with one another because these 2 sort of pictures don't agree. On the right, in X-rays, most black holes are near maximally spinning. On the left, from gravitational wave merger in spirals, most black holes are either not spinning or not aligned. And we think that they should have formed roughly the same way. On the right, we've got in X-rays, remember that's a black hole stealing material from a companion star. If that's a massive companion star, it might someday turn into a black hole, in which case those 2 black holes could eventually merge. So why would that scenario show a different spin or agreement between the spin of those 2 objects compared to the mergers that we have? The real answer is we don't actually know. That's why it's a current debate. The other real answer is, again, these are not the same 2 things. We might have just found a bunch of merging black holes that weren't aligned, or the black hole mergers don't form in the same way as your standard stellar mass black hole with a companion that we look at here in the Milky Way. I should also mention, in the case of my black hole that I've been working with, I haven't measured the spin. I can't measure the spin. My current data set's not good enough unless I make a bunch of assumptions which are probably wrong. And I don't want to make those assumptions. So in my data set, I can't actually measure the black hole spin. The only reason that we have all of these is from decades of observing these sources in a lot of different situations with different telescopes, and by using different models that we were able to come up with this sort of library of black hole spins. Unfortunately, it's not a perfectly straightforward process. So back to the original question, do black holes spin? Yes, very rapidly. And we measured that over and over again over decades using X-rays and using that reflection off of the inner accretion disk that gives us that line profile that we can then measure the inner accretion disk and the black hole spin with. Binary black holes, however, don't appear to spin together. They're either not in tow, not on the same beat, or They're just those black holes are formed in a different way that they don't happen to be rapidly spinning at all. Again, I think there's probably a difference between something that we're actively trying to figure out now. How do you get to a binary black hole, two black holes that merge together, orbit one another and then merge, versus how do you just get a black hole and a normal star that will orbit one another so that the black hole can steal material. Finally, do black holes get dizzy? Well, I would say you could go and ask, but even if you could, and if the black hole, the singularity at the center of the black hole understood our language, it wouldn't be able to tell us because you can't get a signal from inside the event horizon. So unfortunately, we'll probably never know. However, we do know we can measure their spin thanks to the frame dragging effect and the measurements that we've made. I think it's probably a good thing that black holes spin because the spin of a black hole is going to be partially responsible, if not fully responsible, for launching those jets. In the Milky Way, these jets could extend for light years. They might crash into a cloud that could start pushing that cloud and into another molecular cloud, start a new round of star formation. But if you look at, remember that jet from M87, that extends for light years outside of its host galaxy, we've begun to realize more and more looking at the properties of these supermassive black holes and the galaxies that they live in. And we see that a lot of those properties align. The mass of the central black hole and the mass of the galaxy agree for a whole huge host of galaxies and black holes. We think that the jet of the black hole is actually helping create star formation in its host galaxy as that black hole actively grows, which means the black hole is partially responsible for creating new stars, and around those stars for creating planets and possibly creating life. And when that black hole is done, it's possible that it could push away the rest of that remnant gas out into outside the galaxy and turn off star formation entirely. So I think it's probably a good thing that black holes are spinning as long as they agree to be happy about it and help stars form in the process. And that's all I have. Thank you all so much.